Solar power forecasting represents the systematic prediction of future electrical output from photovoltaic (PV) systems across defined time horizons, transforming solar energy from an inherently intermittent resource into a dispatchable, manageable asset. This predictive capability has become indispensable in modern energy systems as solar installations proliferate worldwide. At its core, solar forecasting estimates electricity generation by analyzing multiple interconnected factors: solar irradiance in its various forms, direct normal irradiance, diffuse horizontal irradiance, and reflected irradiance, atmospheric conditions including cloud cover dynamics, aerosol concentrations, and humidity levels, system-specific characteristics such as panel orientation angles, conversion efficiency, and performance degradation over time, and environmental conditions including temperature effects and shading impacts from surrounding structures or vegetation. Beyond mere generation prediction, contemporary forecasting serves as a critical control and optimization input that enables sophisticated energy management decisions. It allows operators to adjust battery charge and discharge schedules proactively, align household or commercial loads with anticipated solar availability, minimize PV curtailment, which represents wasted clean energy generation potential, and optimize grid interaction including import and export decisions. Without accurate forecasting, system operators must rely on conservative assumptions that inevitably lead to excess reserve capacity, inefficient battery utilization, and increased solar curtailment, all of which undermine the economic and environmental benefits of solar energy. The importance of solar power forecasting cannot be overstated in today's energy landscape. Solar energy's inherent intermittency poses significant challenges for grid operators and energy system managers. Cloud cover can change rapidly, causing steep power ramps that are difficult to anticipate and manage without reliable predictive capabilities. These rapid changes constrain grid infrastructure, require excessive reserve capacity to maintain stability, and lead to missed opportunities for optimal solar utilization. Accurate forecasting enables anticipatory control, allowing energy systems to act before variability manifests rather than reacting to it after the fact. This proactive approach is particularly valuable in energy management systems, EMS, where solar forecasts serve as a core decision variable. Within advanced EMS platforms, forecasts enable battery charging during periods when excess PV generation is expected, load shifting toward periods of high solar availability, and reduced grid imports during high-price electricity periods. When combined with time of use, tariffs or dynamic pricing structures, forecasting directly translates into significant cost savings and emissions reductions. For grid operators and market participants, forecasts support critical functions including unit commitment and dispatch decisions, reduction of balancing costs and reserve requirements, and improved accuracy of renewable energy market participation, ultimately contributing to both grid reliability and market efficiency. Methodological approaches to solar forecasting. All solar forecasting techniques ultimately derive from three methodological foundations: physical methods, statistical methods, and holistic integrated approaches. Physical forecasting methods model the physics of the atmosphere and solar radiation to predict irradiance and resulting PV output. These approaches leverage sophisticated numerical weather prediction (NWP) models, satellite imagery that captures cloud motion and cloud optical depth, ground-based sky cameras for localized cloud tracking, and fundamental solar geometry calculations combined with atmospheric transmittance models. The primary strength of physical methods lies in their strong theoretical basis and their effectiveness for medium and long-term forecast horizons. They are highly scalable across large geographic areas and provide robust predictions when atmospheric conditions are relatively stable. However, physical methods have notable limitations. They demonstrate lower accuracy for very short-term forecasts where cloud dynamics evolve more rapidly than model update cycles can capture. They are sensitive to errors in cloud modeling including cloud height, thickness, and motion predictions, and they require substantial computational resources, making them relatively expensive to implement and operate. Despite these limitations, physical methods remain the backbone of medium to long-term solar forecasting, particularly when enhanced with statistical post-processing techniques. Statistical forecasting methods infer future generation from historical and real-time PV output data, often serving to correct or refine outputs from physical models. Common techniques within this category include persistence forecasting, the simplest but often highly effective approach for very short time horizons, regression models that establish mathematical relationships between input variables and PV output, time series analysis techniques that identify patterns in historical data, and machine learning models when trained using statistical approaches. Persistence forecasting operates on the fundamental assumption that near-future solar output equals current output, which may appear simplistic but proves highly effective for very short horizons, typically minutes, and serves as a widely used benchmark model against which more complex methods are evaluated. The strengths of statistical methods include their speed of execution, their data-driven nature that allows them to learn from actual performance, and their high accuracy in stable weather conditions where patterns are consistent. However, statistical methods exhibit significant weaknesses. They perform poorly during rapid weather changes where historical patterns no longer apply. They have limited extrapolation capability when confronted with novel conditions outside their training data, and they typically require substantial historical data for effective training and may struggle with new installations where such data is unavailable. These limitations have driven the development of more sophisticated approaches that combine physical and statistical methodologies. Holistic and integrated forecasting methods represent the most advanced approach to solar power forecasting, combining physical weather models, statistical corrections, real-time asset performance data, and market and tariff information within a forecast-driven energy management system. This integration treats the entire energy system as a closed-loop optimization problem that is continuously updated in real time. Typical EMS inputs include rooftop PV production data, battery state of charge and degradation models, household or industrial load profiles, electricity prices and grid constraints, and both weather forecasts and nowcasts. The decision outputs from this integrated approach include optimized battery charging and discharging schedules, grid import and export timing recommendations, load prioritization strategies, and curtailment avoidance tactics. This holistic approach acknowledges that solar forecasting cannot exist in isolation. Rather, it must be actionable intelligence embedded within a broader energy management framework. By synchronizing solar availability predictions, load demand forecasts, storage capacity constraints, and price signals, integrated forecasting enables truly intelligent energy operation that maximizes economic benefits, enhances system reliability, and minimizes environmental impact. The complexity of these systems reflects the reality that modern energy systems are highly interconnected, and optimization requires consideration of all relevant factors simultaneously rather than treating solar forecasting as a standalone activity. Forecasting horizons, challenges, and implementation considerations. Solar power forecasting horizons define when predictions apply rather than how they are produced, with different horizons serving distinct operational and strategic purposes. Short-term forecasting encompasses nowcasting, seconds to approximately 2 hours, and intraday forecasting, hours ahead. Nowcasting utilizes real-time sensors, sky imagers, and satellite motion vectors to provide ultra-short-term predictions essential for voltage regulation, ramp rate control, and fast battery response actions that must occur on timescales of seconds or minutes. Intraday forecasts, covering hours ahead, support load following, congestion management, and intraday market trading activities. For grid operators, the benefits of accurate short-term forecasting include improved frequency control and reduced activation of reserve capacity. For generators, these forecasts enable higher market accuracy and reduced imbalance penalties. Day-ahead forecasting covers the 24 to 48-hour horizon and is critical for energy market bidding, maintenance scheduling, and demand planning. These forecasts typically blend NWP models with statistical post-processing to balance the strengths of physical and statistical approaches. Medium and long-term forecasting extends from week-ahead to seasonal and year-ahead horizons, supporting fuel procurement planning, energy purchase contract optimization, seasonal capacity planning and resource adequacy assessments, infrastructure investment decisions, policy and tariff design, and capacity expansion planning. These longer-term forecasts rely primarily on climatological data corrected for known biases, recognizing that long-term predictions necessarily involve greater uncertainty but remain essential for strategic planning. Specialized forecasting approaches address particular needs that conventional forecasts cannot adequately serve. Spatial forecasting accounts for geographic irradiance variability, which is essential for managing distributed PV fleets spread across diverse locations and for regional grid planning where local conditions can vary significantly. Uncertainty forecasting provides probabilistic outputs including confidence intervals rather than single-point deterministic predictions, enabling risk-aware decision-making that acknowledges the inherent uncertainty in solar generation. This probabilistic approach is critical for reserve planning where grid operators must maintain adequate margins to accommodate unexpected variations, and for financial hedging where market participants need to understand the range of possible outcomes rather than rely on a single predicted value. These specialized approaches reflect the maturation of solar forecasting from a relatively simple prediction activity to a sophisticated discipline that addresses the complex realities of modern energy systems. The ability to quantify uncertainty and account for spatial variability represents significant advances in the field and enables more sophisticated and robust energy management decisions. Despite substantial advances in solar forecasting technology, significant challenges persist that limit forecast accuracy and reliability. Intermittency remains the fundamental challenge. Rapid changes in cloud cover cause steep power ramps that are difficult to predict precisely regardless of the methodology employed. Weather data uncertainty compounds this challenge, as errors in cloud height, thickness, or motion propagate directly into PV forecast errors, creating a cascade effect where initial measurement or modeling inaccuracies magnify through the forecasting process. Solar curtailment represents a particularly pernicious challenge. Without accurate forecasts, batteries may fail too early when solar availability was overestimated, grid export limits may be exceeded when generation exceeded predictions, and clean energy is wasted due to suboptimal scheduling decisions. Spatial variability introduces additional complexity, as localized shading, terrain effects, and microclimates require high-resolution data and sophisticated models that may not be available or affordable for all installations. These challenges are not merely academic. They have real economic and environmental consequences in terms of reduced renewable energy utilization, increased system costs, and higher emissions when backup generation must compensate for forecast errors. Addressing these challenges requires ongoing research, improved data collection infrastructure, and the development of more sophisticated modeling approaches that can capture the complex, nonlinear dynamics of solar energy generation. Solutions, implementation, and future directions. Addressing the challenges in solar power forecasting requires a multifaceted approach that combines technological innovation, improved data availability, and system-level optimization. Advanced forecasting models represent the forefront of solution efforts, incorporating machine learning and hybrid physics AI models that can capture complex nonlinear relationships that purely physical or purely statistical approaches cannot adequately represent. Bias correction techniques and ensemble forecasting methods help mitigate systematic errors and provide more robust predictions by combining multiple models and accounting for their individual strengths and weaknesses. Continuous model retraining ensures that forecasting models remain accurate as conditions change, system components degrade, and operating patterns evolve over time. High-frequency weather data, with sub-hourly or even sub-minute updates, improves responsiveness and enables rapid re-optimization of energy systems as conditions change. This increased temporal resolution is particularly valuable for short-term forecasting where cloud dynamics can evolve rapidly. Smart meter integration provides real-time load visibility, enables accurate demand forecasting, and facilitates better matching of PV generation with consumption patterns. Together, these solutions address the core challenges in solar forecasting and enable more accurate, reliable, and actionable predictions that can be embedded within energy management systems to drive optimization decisions. The implementation of solar forecasting within an energy management system represents the practical application of all the theoretical and methodological advances discussed. Within an EMS, solar forecasting is not standalone, it becomes actionable intelligence that drives real-world operational decisions. An EMS uses forecasts to minimize energy costs under time of use or dynamic pricing tariffs, maximize self-consumption of locally generated solar energy, reduce emissions by optimizing the mix of solar, storage, and grid power, extend battery life through optimized charge and discharge scheduling, and improve grid stability by providing predictable, manageable solar generation profiles. By synchronizing solar availability predictions with load demand forecasts, storage capacity constraints, and price signals, forecasting enables truly intelligent energy operation that would be impossible without accurate predictive capabilities. The EMS acts as the brain that processes forecast information and translates it into concrete actions such as when to charge or discharge batteries, when to shift loads, and when to import or export power from the grid. This closed-loop optimization, continuously updated with new forecast data, represents the state-of-the-art in solar energy management and demonstrates how forecasting transforms solar from an intermittent resource into a strategically optimized energy asset. Looking to the future, solar power forecasting will continue to evolve in response to increasing penetration of solar energy in power systems worldwide. Advances in satellite technology, including higher spatial and temporal resolution, will provide more accurate inputs to physical models. Improvements in machine learning algorithms and computing power will enable more sophisticated hybrid approaches that can process larger datasets and capture more complex relationships. The proliferation of smart meters and other IoT devices will provide richer real-time data that can be used to improve forecast accuracy, particularly at the distribution system level. Integration of solar forecasting with other renewable resources, including wind and storage, will become increasingly important as the energy system becomes more diverse and interconnected. Standardization of forecast products and metrics will facilitate their use by grid operators, market participants, and other stakeholders. Perhaps most importantly, the continued development and deployment of solar forecasting capabilities will be essential for achieving the full potential of solar energy as a cornerstone of sustainable, reliable, and affordable power systems. The transformation of solar from a variable, unpredictable resource to a dispatchable, optimized asset represents one of the most significant technical achievements in modern energy systems, and ongoing advances in forecasting technology will be central to realizing this vision.